again. We're going to talk about colligative properties in this video. So first thing, colligative properties are properties of a solution that depend on the concentration of the solute. So we've been talking and discussing a lot about solutions and solutes and concentration. However, these properties are not the identity of the solution. So the number of dissolved solute particles affect colligative properties, okay? But the identity of the solute does not. Okay, so it doesn't matter really what the solute is for these properties. Okay, it's just the amount of dissolved solutes that are present. Okay, so this is going to be something that it's going to come up when we work a couple of problems, and these problems we're going to work are very similar to your homework. So right now I just want you to remember or to think about it this way. Okay, so if we have something like potassium iodide in water, for example. Okay, what this is saying is that the number of particles affects the properties that we're about to discuss. Okay, so let me go ahead and tell you what those properties are. Okay, the elevation of boiling point, okay, the lowering of melting point, and also pressure, which we're not going to cover in this video. Okay, so the colligative properties here that we're looking at in this video is the elevation of the boiling point and the lowering of the melting point. Okay, so if we think about water, we know that its boiling point is 100 degrees C. Okay, so if we think about what we're looking at here, we're looking at situations where the colligative properties and the solute in number of particles are going to elevate the boiling point or lower the melting point. So if you have a situation here, we have potassium iodide. This is an ionic compound. So we discussed earlier in some previous videos that when we place potassium iodide in water, it dissociates into its constituent ions, right? So in solution in water, okay, and so if we're in water here, we have potassium ion. Okay, remember it's in group 1, so it has a +1 ionic charge. And then iodide is a halogen, right? So it has a -1 charge because it wants to gain 1 electrons. So here we actually have from this 1 mole here of Ki, we have 2 particles that are going to be present in our solution. Okay, so I want you to go ahead and think about this as we're moving through this topic. Okay, so let's look at boiling point elevation. Okay, and first thing I wanted to discuss is, what does volatile mean? Most of us have heard this term, whether it be someone has a volatile personality or a substance is volatile. Okay, this means that the solute readily escapes into the vapor phase. So I kind of think about it as it's volatile. It wants to leave. It wants to go into the vapor or the gas phase. It wants to escape. Okay. A non-volatile solute does not want to escape. So it has really a negligible vapor pressure at a given temperature. Okay, so the vapor pressure above a solution of a non-volatile solute is lower than the vapor pressure of the pure solvent. Okay, let's think about this. Okay, a lot of students get this backwards. Okay, but it actually does make sense. So if you know what volatile means and you understand what pressure and vapor pressure means, then it does make sense. Okay, so if you have a non-volatile solute, okay, that means it does not want to escape, right? So if it's not wanting to escape into the gas phase, then it has a low vapor pressure. It's not building up pressure because it's not volatile, right? It doesn't want to escape, okay? If you have a volatile solute, then the opposite's going to be true, right? So if you put a solute into water and it's very volatile, then the pressure, the vapor pressure, is going to be higher, right? So the vapor pressure is going to be high because it's exerting more pressure because a volatile solute wants to escape. right? So if it wants to escape and go to the gas phase, it's going to build up pressure. So if what boiling point elevation means is that if we have a liquid solution that contains a non-volatile solute, it's going to have a higher boiling point, okay, than the solvent alone. Okay, so like I said, students sometimes get this reversed, but if you think about it, if a non-volatile solute, okay, does not want to escape, right? So it non-volatile, look back at what that means. It does not readily escape, so it has a negligible vapor pressure, okay? All right, so if it doesn't want to escape and it doesn't want to boil, right, then it's going to have a higher boiling point, okay, than the solvent alone. Okay, so if you have water and you add table salt to it, okay, the boiling point of that salt water is going to go up. It's going to be higher than 100 degrees because you're adding some non-volatile solute to the water, okay? The amount that the boiling point increases depends on the number of dissolved particles. And so this is what I was discussing earlier. If you have potassium iodide, okay, technically it's two particles. You have potassium ion and you have the iodide anion. Okay, so we have a sort of rule here that we can use. If you have 1 mole of a non-volatile solute, okay, it's going to raise the boiling point of 1 kilogram of water the same amount. Okay, so it doesn't matter what that's what it was talking about earlier when we said colligative properties are not the identity. Okay, that's because we can use any non-volatile solute. Okay, and it's going to raise the boiling point of 1 kilogram of water the same amount by 0.51 degrees C. Okay, so non-volatile solutes, that means they do not want to escape, right? They do not want to escape into the vapor phase. Okay, therefore, they raise the boiling point of your solution. Okay, freezing point is sort of the same idea. Okay, a liquid solution that has a non-volatile solute, again, is going to have a lower freezing point than the solvent alone. Okay, so here boiling point is going to be higher. Okay, it's going to have a higher boiling point when you add non-volatile solutes, and the freezing point is going to be lower when you add non-volatile solutes. Okay, and this also depends on the number of particles. Okay, and for 1 mole of any non-volatile solute, the freezing point of 1 kilogram of water, it's going to be lowered by 1.86 degrees C. All right, if you're in my class, you're getting to use a flashcard for this section instead of memorize this. So this may be one thing that you want to put on there. So be sure you remember these numbers. So boiling point elevation is 0.51 degrees C. Okay, is what it raises 1 kilogram of water, and then lowers the freezing point by 1.86 degrees C per kilogram of water. Okay, so let's do some practice because there's a common mistake that happens with these problems, and it's real easy to fix and to see, but definitely need to practice these. So if we want to know what's the boiling point of a solution that contains the following quantity of solute, okay, in 1 kilogram of water. Okay, so if we're looking at boiling point and we're adding a non-volatile solute to it, we know that our boiling point is going to go up. Okay, and so by how much, you can look back if you would like, but we saw on the previous slide that the temperature, the boiling point is going to go up by 0.51 degrees per mole, right? So that was per 1 mole. All right, so I kind of started in the middle here on accident, but so we have 3.6 moles is what we're given in our problem. Okay, so we always write out what we're given. I went ahead and wrote out what my conversion factor was first. Okay, but we want our moles to cancel. Okay, so if we have 3.6 moles, and then we know that per mole, or per kilogram, so we have 1 kilogram there, okay, then we know that 3.6 times the 0.51, you would think that that would be where we would stop. That would be enough. Just multiply 0.51 times 3.6. Okay, the problem is what we mentioned earlier. If you have Ki, okay, these colligative properties depend on the number of dissolved particles. And remember, I told you that we have 2 dissolved particles for every mole. Okay, so the last thing we have to do is multiply by 2 mole particles, is what we call them. All right, and that will give us an answer of 3.67 degrees. Looks like we have 2 sig figs, so we'll have to round that up. Okay, this is the temperature, how much the boiling point is elevated. Okay, so if we know that boiling point of water is normally 100 degrees C, and so with 3.6 moles of Ki, it's raised by we'll go ahead and round that to 3.7 degrees. And so our answer is 103.7 degrees C. Okay, so the answer you get here is how much the temperature goes up. And then we know that the boiling just water is 100, so instead of just being 100 degrees, if we add 3.6 moles of potassium iodide to it, now the temperature is going to go up to 103.7 degrees. All right, for our freezing point, we do the same type situation. We have 3.9 moles this time. We know for every mole, and really we have per kilogram. Okay, this time if you look back at your slide, the temperature decreases by 1.86 degrees C. Okay, and then once again we have 2 mole particles. Okay, and so this is different from what we've been seeing because this is a colligative property and it depends on the number of dissolved particles. Okay, and so we get 14.5 degrees C. Okay, we know that the freezing point of water is 0 degrees. So so you have to remember here that you're subtracting. So this is lowering. If you want to put a negative there, you can, but you're going to lower the freezing point by whatever your answer is here. Okay, and so the answer would be negative 14.5 degrees C. So the freezing point when you add 3.9 moles of Ki is significantly lower than if it was just water. All right, another way to think of this, a good example, is when they salt the roads. Okay, this is the idea behind that. So when we have snow and ice, which is not too common here in Alabama, but when it does happen, when they add salt to the roads, this is the idea behind that. So when you add in a non-volatile solute, okay, you're going to lower the freezing point, okay, and that would be a good thing for icy roads. Okay, and so so if you add the non-volatile salt and salt the roads, then the freezing point decreases, and that's a good thing, right? Because if it's just 0 degrees but then we've lowered the freezing point to negative 14, okay, then it's less likely that the roads will freeze unless the temperature drops that much more to get down to the lower temperature. All right, hope this helps, and I will see you soon.